Welcome to today's ArXiv Computer Science Digest for May 22nd, 2026. We received 688 new computer science papers today across 56 subfields. Let's dive into the top picks. Trend 1 of 10, AI Education and Explainability. Advancing AI in education through improved understanding, evaluation, and explainability. This cluster covers 72 papers. Representative work includes SPACENUM, Revisiting Spatial Numerical Understanding in VLMs, toward an evaluation methodology for AI in second language education. Lessons learned from developing L2 bench and strong teacher not needed. On distillation in LLM pre-training. Trend 2 of 10, Video Generation and Alignment. Advancing video generation through alignment, insertion, and hybrid neural representation techniques. This cluster covers 35 papers. Representative work includes Geo-Align, video generation alignment via metric geometry reward, Smart-Insertion-V, Photorealistic video insertion via a closed-loop feedback dual-stream framework, and RT-NeRV, rethinking hybrid neural representation for video via residual tokenization. Trend 3 of 10, LLM Capacity and Trustworthiness. Exploring the limits and reliability of large language models in capacity and trustworthiness. This cluster covers 73 papers. Representative work includes LLMs as noisy channels, a Shannon perspective on model capacity and scaling laws, ETCHR, editing to clarify and harness reasoning, and is capability a liability? More capable language models make worse forecasts when it matters most. Trend 4 of 10, Model Optimization and Dynamics. Advancing model efficiency, adaptability, and dynamic behavior through novel optimization and simulation techniques. This cluster covers 78 papers. Representative work includes PGT, procedurally generated tasks for improving visual grounding in MLLMs. Muon, a Hamiltonian probability gradient flow perspective of Muon optimizer, and learning a particle dynamics model with real-world videos. Trend 5 of 10, Causal Modeling and Robotics. Integration of causal reasoning and robotic learning for improved perception, control, and interaction. This cluster covers 65 papers. Representative work includes optimal vector balancing for zonotopes, leveraging foundation models for causal generative modeling, and instrumentation for imitation learning, enhancing training datasets for close-hanger insertion. Trend 6 of 10, Skill Learning and Causality. Advancing skill acquisition and causal understanding through AI and machine learning. This cluster covers 34 papers. Representative work includes from raw experience to skill consumption, a systematic study of model-generated agent skills, from activation to causality, discovery of causal visual representations in the human brain, and good token hunting, a hitchhiker's guide to token selection for visual geometry transformers. Trend 7 of 10, Diffusion and Decision Modeling. Combines diffusion models and decision-making frameworks to enhance learning and reasoning. This cluster covers 62 papers. Representative work includes PID, fast and high-resolution latent decoding with pixel diffusion, human decision-making with persuasive and narrative LLM explanations, and R3L, reflect then retry reinforcement learning with language-guided exploration, pivotal credit, and positive amplification. Trend 8 of 10, Language Model Distillation. Advancing efficient and secure language model training and deployment through knowledge distillation and model analysis. This cluster covers 67 papers. Representative work includes entropy-aware on-policy distillation of language models, training free loop transformers, and benchmarking commercial ASR systems on code-switching speech, Arabic, Persian, and German. Trend 9 of 10, Agent Skills and 3D Learning. Advancing agent capabilities and 3D scene understanding through skill optimization and reconstruction techniques. This cluster covers 183 papers. Representative work includes SkillOpt, executive strategy for self-evolving agent skills, a two-branch finite field construction for regular CSS LDPC bases, and complete MUI, optimal hyperparameter transfer and scaling for MO models. Trend 10 of 10, Interpretability and Optimization. Advancing model interpretability and optimization techniques across diverse domains. This cluster covers 19 papers. Representative work includes multilingual knowledge transfer under data constraints via lexical interventions, enhancing energy efficiency in scientific workflows through CFD-based PVIs, and mechanistic interpretability of EEG foundation models via sparse autoencoders. Up next, our first paper out of 10, MedVIGIL, Evaluating Trustworthy Medical VLMs Under Broken Visual Evidence by Hanqi Jiang and Xiang Li from University of Georgia. This paper was selected because it introduces a novel and critical evaluation framework for medical vision language models, addressing the pressing issue of model trustworthiness in safety-critical clinical settings by identifying and mitigating silent failures under corrupted evidence. Let's break down its key contributions. Contribution 1. MedVIGIL Evaluation Suite. MedVIGIL is a 300-case evaluation suite for medical VLMs, containing 2,556 MCQ probes and 240 counterfactual triplets. It is built using clinician-authored content, including gold answers, ROI boxes, and risk tier annotations, supervised by 4 board-certified radiologists. The dataset is publicly released and provides a human reference baseline with an MCS of 83.3, showing a 14.1-point headroom over the best audited model. Contribution 2. Silent failure detection. Silent failures are identified when models provide fluent answers despite corrupted evidence like false premises or ROI-corrupted images. The method uses perturbed evidence scenarios, including false premises, wording perturbations, and knowledge-only rewrites, to test model robustness. The benchmark reveals that the best model, Claude Opus 4.7, has a silent failure rate of 30.8% compared to 5.8% for the human baseline. Contribution 3. MedVIGIL Composite Score, MCS. MCS is a composite metric summarizing 7 correctness-conditioned audit metrics for evaluating medical VLMs. It is derived from 7 audit metrics that assess model performance across different types of corrupted evidence and risk tiers. The human baseline achieves an MCS of 83.3, while the best model scores 69.2, showing a 14.1-point gap in clinical trustworthiness. Contribution 4. Clinician-adjudicated annotations. Physician-adjudicated annotations include risk tier flags, answerability flags, and ROI boxes for all 300 cases in MedVIGIL. Annotations are produced by 2 attending radiologists in parallel, with a senior radiologist consolidating the final manifest. This ensures high-quality, clinically relevant evaluation data, with a human reference baseline that reflects real-world clinical judgment. Contribution 5. Open-ended variant and counterfactuals. Open-ended variants and 240 counterfactual triplets are included to test model reasoning and consistency under corrupted inputs. The counterfactual triplets evaluate how models respond to paraphrased or false premise questions paired with original or altered images. These components enhance the benchmark's ability to detect unsafe model behavior in ambiguous or misleading clinical scenarios. Up next, our second paper out of 10, Robust Counterfactual Inference in Markov Decision Processes by Jessica Lally and Nicola Paletti from King's College London. This paper was selected because it introduces a novel and robust framework for counterfactual inference in Markov decision processes, addressing a critical limitation in existing methods by accounting for multiple plausible causal models, thereby significantly enhancing the validity and applicability of counterfactual reasoning in decision-making systems. Let's break down its key contributions. Contribution 1. Non-parametric counterfactual bounds. Tight bounds on counterfactual transition probabilities across all compatible causal models are computed. The method uses closed-form expressions instead of solving large-scale optimization problems, reducing computational complexity. This results in highly efficient computation for large-scale MDPs, enabling scalability beyond prior methods. Contribution 2. Interval counterfactual MDP construction. Interval counterfactual MDPs are constructed using the computed probability bounds. The intervals represent uncertainty in transition probabilities due to causal model ambiguity. This allows for robust policy evaluation by accounting for worst-case scenarios and counterfactual outcomes. Contribution 3. Robust counterfactual policy optimization. Robust counterfactual policies are identified by optimizing the worst-case reward over the interval MDP. The optimization leverages worst-case reward maximization to ensure performance under uncertainty. This leads to improved robustness compared to existing methods, in case study evaluations. Up next, our third paper out of 10, SWEVO, Benchmarking Coding Agents in Long-Horizon Software Evolution Scenarios by Tuesday Lu and Guy D. Q. Bui from FPD Software AI Center, Hanoi, Vietnam. This paper was selected because it introduces a novel and highly relevant benchmark for evaluating AI coding agents in realistic, long-horizon software evolution scenarios, addressing a pressing challenge in systems and AI-driven software development. Let's break down its key contributions. Contribution 1. SWEVO Benchmark Creation. SWEVO benchmark for long-horizon software evolution tasks was constructed. It includes 48 tasks from 7 open-source Python projects, each requiring multi-step changes across 21 files on average. Each task is validated against a test suite with 874 tests per instance, ensuring functional correctness. Contribution 2. Performance evaluation of AI agents. GPT 5.4 with OpenHands achieved only 25% success rate on SWEVO. This performance is significantly lower than 72.8% on the simpler SWE-bench verified tasks. The drop highlights a capability gap in handling complex, multi-file, long-horizon software evolution. Contribution 3. Fixed-rate metric introduction. Fixed-rate was proposed to measure partial progress in long-horizon tasks. It captures the ability of agents to make incremental improvements rather than full task completion. This metric provides a more nuanced evaluation of agent performance in complex software evolution scenarios. Up next, our fourth paper out of 10, Mitigating Object Hallucinations via Sentence-Level Early Intervention by Shangping Peng and Zhuotao Tian from Harbin Institute of Technology, Shenzhen. This paper was selected because it introduces a novel and effective approach to mitigating hallucinations in multimodal large language models by intervening early in the text generation process, which is a critical and pressing issue in the deployment of LLMs for real-world applications. Let's break down its key contributions. Contribution 1. Sentence-Level Early Intervention Framework. Sentinel reduces hallucinations by over 90% compared to the original model. Sentinel uses context-aware preference learning with CDPO loss to focus on sentence-level discriminative learning. This results in superior performance over prior state-of-the-art methods on hallucination and general capability benchmarks. Contribution 2. In-domain preference data construction. High-quality in-domain preference pairs are bootstrapped using model outputs and open vocabulary detectors. The method iteratively samples, cross-checks object existence, and classifies sentences as hallucinated or non-hallucinated. This eliminates the need for human annotations and reduces domain discrepancy in training data. Contribution 3. Context-aware discriminative learning. CDPO loss emphasizes learning at the sentence level where hallucinations first appear. The loss function uses context-coherent positive samples and hallucinated negative samples to improve discrimination. This leads to 90% fewer hallucinations and better generalization across benchmarks. Up next, our fifth paper out of 10, Broken Memories, Detecting and Mitigating Memorization in Diffusion Models with Degraded Generations by Yuanmin Huang and Min Yang for Fudan University. This paper was selected because it introduces a novel and critical insight into the memorization behavior of diffusion models, offering a principled method to detect and mitigate this issue, which has significant implications for privacy, copyright, and the safe deployment of generative AI systems. Let's break down its key contributions. Contribution 1. Memorization detection via stability analysis. AUC greater than 0.999 detection performance on stable diffusion 1.4. Empirical stability regions based on latent update norms identify numerical instability caused by memorization. Outperforms prior methods by enabling stepwise detection with minimal computational overhead, is almost equal to 0.01 S per image. Contribution 2. On-the-fly adaptive mitigation framework. 0% memorization rate after mitigation on stable diffusion 1.4. Adaptive mitigation dynamically adjusts generation without altering prompts or guidance. Achieves 0 memorization while preserving semantic fidelity and image quality, unlike prior static or heuristic methods. Contribution 3. Numerical stability as a memorization indicator. Numerical instability in diffusion models is linked to memorization for the first time. Latent update norms are used to quantify instability during generation. Provides a quantitative and generalizable approach to detect memorization, improving over prior visual or sample-based comparisons. Up next, our 6th paper out of 10, PhenoYieldNet. Learning crop-aware phenological responses for multi-crop yield prediction by Yu Luo and Kuan, who from the University of Sydney. This paper was selected because it introduces a novel, crop-aware framework for multi-crop yield prediction that explicitly models phenological responses to weather, addressing a critical challenge in global food security with broad applicability in agricultural AI. Let's break down its key contributions. Contribution 1. Crop Phenology Bank, CPB. Crop Phenology Bank learns crop-specific phenology patterns using learnable embeddings. The CPB uses a query mechanism to guide the selection of relevant phenology patterns for each crop. This enables multi-crop generalization with improved accuracy over single-crop models. Contribution 2. Crop Phenology Attention, CPA. Crop Phenology Attention module captures multi-scale trend and variation components. The CPA dynamically adjusts attention across different phenological stages using temporal contexts. This leads to 20% higher accuracy in yield prediction compared to prior methods. Contribution 3. Temporal Contrastive Adaptation. Temporal contrastive adaptation aligns pre-trained models with agricultural temporal dynamics. The self-supervised strategy enhances feature generalization across diverse crops and regions. This results in 15% better performance on unseen regions and crops. Up next, our 7th paper out of 10, Joint Targetless Intrinsic and Extrinsic Camerly-DR Calibration using Deep Point Correspondences by Simon Boltman and Abhinav Aleda from University of Freiburg. This paper was selected because it introduces the first fully targetless pipeline for joint intrinsic and extrinsic Camerly-DR calibration using deep point correspondences, addressing a critical challenge in multimodal perception for robotics and autonomous systems. Let's break down its key contributions. Contribution 1. Joint Targetless Calibration. Joint Camerly-DR calibration with unknown intrinsics and extrinsics. Deep pixel point correspondences and nonlinear optimization are used to jointly estimate parameters. Achieves improved extrinsic accuracy and recovers accurate intrinsics on the KITTI dataset. Contribution 2. Automatic Intrinsic Initialization. Automatic Intrinsic Initialization using Structure for Motion, SFM. Synchronized camera images are used to estimate initial intrinsics without manual input. Reduces initialization error and enables robust calibration in uncontrolled environments. Contribution 3. Generalized Deep Correspondence Learning. Deep correspondence learning generalized to raw images with unknown intrinsics. Pixel point matching is adapted to handle radial tangential distortion and unrectified images. Enables target-less calibration in real-world scenarios with varying camera setups. Contribution 4. Tightly coupled optimization. Tightly coupled iterative optimization over intrinsics and extrinsics. Deep correspondences are iteratively refined with nonlinear optimization to improve calibration. Leads to higher calibration accuracy compared to decoupled or target-based methods. Up next, our 8th paper out of 10, Towards Generalizable and Efficient Large-Scale Generative Recommenders by Qiuling Su and Mamitabh Bhattacharya from Netflix Research. This paper was selected because it addresses a critical and underexplored challenge in large-scale generative recommendation systems, demonstrating practical and scalable solutions in a real-world industrial setting with millions of users. Let's break down its key contributions. Contribution 1. GenRank Architecture for Ranking. GenRank achieves significant user satisfaction improvements in Xiaohongshu's Explore feed. It uses a generative architecture that leverages the inherent sequential modeling of user behavior for ranking. Online A/B experiments show 22.5% relative gain on lower predictability tasks compared to the baseline. Contribution 2. Multi-token prediction for latency alignment. Multi-token prediction is introduced to align serving latency in generative recommenders. This mechanism enables efficient decoding by predicting multiple tokens at once, reducing computational overhead. It ensures nearly equivalent computational resources compared to existing systems while improving performance. Contribution 3. Semantic item towers for cold start adaptation. Semantic item towers are used to score newly launched items using metadata. This approach avoids reliance on collaborative ID embeddings during cold start phases. It improves item generalization and enables reliable scoring for new items before collaborative signals are available. Contribution 4. Scaling laws for task-specific model capacity. Scaling laws are applied to analyze task-dependent model capacity in generative recommenders. The method uses offset scaling law fits to diagnose where additional model scale is beneficial. A 1B backbone model outperforms a 2M backbone baseline across all tasks in a production shadow evaluation. Contribution 5. Efficient repeated training with sampled softmax. Sampled softmax and a projected decoding head are used to reduce repeated training costs. These techniques lower the computational burden of training over trillions of behavior tokens. They enable frequent retraining without sacrificing model performance or increasing resource usage. Up next, our 9th paper out of 10, Imagine 2 Real, Towards Zero-Shot Humanoid Object Interaction via Video Generative Priors by Jiahe Chen and Jingbo Wang from Zhejiang University. This paper was selected because it introduces a novel zero-shot interaction framework for humanoid robots that bridges the morphology gap between humans and robots, enabling versatile object interaction without extensive training or motion retargeting. Let's break down its key contributions. Contribution 1. Zero-shot HOI via video generative priors. Dream 2 ACT enables zero-shot humanoid object interaction with a 37.5% success rate on 4 tasks. It uses video generative priors to synthesize robot native motion in 4D space, bypassing human-centric retargeting. This outperforms conventional retargeting, which achieves 0% success due to morphology gaps and spatial misalignment. Contribution 2. Robot native 4D key point tracking. Imagine 2 Real extracts 4D point trajectories for robot and object motions. It tracks sparse critical points, base, hands, object, to avoid error-amplifying retargeting. This enables morphology-consistent spatial alignment, improving contact formation and task success. Contribution 3. Behavior Foundation Model for Natural Gates. The framework uses a Behavior Foundation Model, BFM, latent space to maintain natural gates. It employs a progressive training strategy with simple tracking rewards to learn robust behaviors. This allows zero-shot deployment in real-world mocap systems with minimal prior training. Up next, our 10th paper out of 10, Construction of ETCHR with Imperfect EBITs by Guanmin Guo and Ruehu Li from Air Force Engineering University. This paper was selected because it generalizes the stabilizer formalism for entanglement-assisted quantum error-correcting codes with noisy EBITs, providing a unified framework for constructing quantum error-correcting codes in qubit systems. Let's break down its key contributions. Contribution 1. Généralise ETCHR framework. QARY ETCHR for qubit systems are constructed using the generalized Pauli group over FQ. The framework leverages symplectic geometry over FQ superscript 2 and additive codes over FQ superscript 2 to unify code construction. This generalization enables high-dimensional quantum error correction with performance comparable to or better than standard stabilizer codes under specific noise conditions. Contribution 2. Equivalent formulations for ETCHR. Equivalent formulations of ETCHR are derived using symplectic geometry over FQ and additive codes over FQ superscript 2. The formulations provide a mathematical bridge between quantum code design and classical coding theory. This allows for simplified analysis and construction of ETCHR in high-dimensional systems. Contribution 3. Performance analysis of QARY ETCHR. Several families of QARY ETCHR with noise EBITs are constructed and analyzed. The performance is evaluated by comparing error-correcting capability with optimal stabilizer codes. Under certain noise conditions, the proposed codes outperform standard stabilizer codes, showing improved fault tolerance in high-dimensional quantum systems. That's all for today's ArXiv Computer Science Daily. If you found this helpful, please leave a comment, and subscribe for daily paper summaries. See you tomorrow.